Good evening and welcome to Tinkering with Edkelar. Following the tube-based project from last episode, I have something from the early digital section again this time. This device, an HP 59401A, is a bus analyzer for the HPIB, the HP Instrument Bus, or more generally known as GPIB, General Purpose Instrument Bus, which is an IEEE standard, IEEE 488 if you like numbers. I'll be using the more modern GPIB name, but HPIB is the groundwork for that standard, so essentially they are the same. Pretty much like SSL and TLS for the computer folk out there. GPIB is a rather old and slow way of connecting digital equipment developed during the 1970s. It is an 8-bit parallel bus that runs at TTL levels and can connect up to 15 devices on the bus. The cables are a bit on the heavy side, using a 24-pin connector that stacks male and female end in one case. That way, daisy chaining of the bus is easy and doesn't require any in and out sockets like SCSI has. In the early days, HP used the bus for all sorts of computer peripherals like tape drives and printers, but over time faster alternatives were introduced there. So test instruments are pretty much the only device category left that still uses GPIB today, but USB and Ethernet is displacing it here too. After finding this unit on eBay, I did a quick search for information and discovered that Curious Mark used it in a repair of an old tape drive. I link to that video below. Now, what can this thing do? It can listen in on the GPIB bus and store up to, brace yourself, 32 bytes of information from the bus for diagnostics. Or, alternatively, you can program a sequence of up to 32 bytes into that same memory and then play it out over the bus. This does limit the application to very low-level diagnostics indeed. Most modern instruments use text-based commands and responses, so 32 bytes is probably at most useful for one comment or reply from those. But once the bus interface works, any further diagnostics is better done on the computer anyhow. I still think this will be handy to check up on misbehaving devices on the bus level. But now, let's jump in! First things first, the unit seems to be in medium good condition. There are a few scuff marks and two of the toggle switches are bent. Clearly, it has been thrown around a bit. The covers come off easily. Oh, and a warning to all US folk. This unit is metric. Nice, spiffy clean on the inside. You gotta love these old units that didn't need a fan. The front panel is attached to the two large PCBs with a card edge connector each. I'm taking off the front in one chunk before taking out the PCBs. The mains switch is the same style as all the other switches, but it is connected with a wire instead of PCB traces. That makes for a bit of awkwardness. I don't want to cut the line, and I can't yet tell where to unplug it. The mains voltage selector uses plugs to connect to the transformer and mains switch. No solder needed so far. The mains input filter has a set of capacitors inside. I checked. While they are probably not Y-rated ones, they are at least not RIFAs. Yay! Getting the plastic trim pieces off the handles was tricky. They are snapped into place with considerable force. After a few more screws, I got the case apart. Oh, there is a RIFA hiding underneath that mounting bracket. Interesting. It is cracked, like to be expected, but it isn't across the mains input. This one is connected across the AC pins of the bridge rectifier. As for recapping, this one is an interesting case. There are several tantalums, which seem to be fine, and 3 regular electrolytics. I'll replace those, but there is also one rather uncommon tube, 4 pins, but just for 1 capacitor inside. Kinda looks like a capacitor wound around a pair of wires. Weird. Recapping. Cleanup time! I'm using a magic eraser again to carefully bring out the shine. The input or trigger switches are grouped for octal input. Somebody labeled them with a bit of scotch tape. Decades ago. That took some elbow grease to remove, but at least it wasn't jotted down on the front panel directly. Let's look at the toggle switches next. They seem to be working fine, but two of them have distinct bends in the pedal. To avoid damaging the mechanism when I try to straighten them, I desolder them and open them up. Darn, these ones need specialty tools to remove the actuator pedal. There is a hinge that holds them in place, and that is pressed in. Whoops! One of the hinge pins came loose when working the switch. Good thing I found it on my desk. Soldering in the switches. To make sure they line up, I put on the front panel before soldering. I have to remake that strange 4-pin capacitor. The two jumpers connect the 5V DC supply to the regulator. The original value was 4500 microfarad, but I found two 2200 microfarad ones. Perfectly adequate to put in parallel. and adding components back to the frame, starting on the rear panel to get the tangle of wires into shape again. I am replacing the RIFA with a regular capacitor of similar size. I am adding a bit of thermal paste on the 5-volt regulator. And here comes the main PCB, part of which is sticking out the rear panel. It provides a set of test points to expose the GPIB bus signals. This is certainly useful to connect a logic analyzer or scope. According to the manual, the device came with a riser board for the front panel connector. Searching for the HP item number, I found one for sale in France. This will be handy if repairs are required. The unit has only one adjustment. the 5-volt rail in the power supply. To adjust it, I plug in the front panel. And nice 5 volts. Interesting detail. HP did take the 5-volt rail very serious. You can see here, the rectified input gets fed into a small capacitor and then, via a choke, into the larger one, the weird 4-pin one. From here, the regulator picks up and creates the 5 volts, again running through an even larger choke. Funny detail, there is CR3 here, which should protect the regulation transistor from back EMF from the choke, and then there is CR2, a 5.6 volt zener to protect against overvoltage should the regulator fail in a short. Not quite a crowbar, but similar. The front panel assembly is simple enough, just a bit odd because the instruction quick reference card is a bit unwieldy. Meh. The reference card slides in and out in a sleeve that is bolted to the main PCB. That way, it doesn't get snagged on the solder joints. The sleeve is torn out though, so it needed a bit of fixing tape first. And after adding the panels, the device is done. Now, how to test it? I think I have the right companion device for this project. This here is a 59303A digital to analog converter. It does take numeric input from the GPIB bus and converts the numbers into a voltage from negative 9.99 volt to positive 9.99 volt in 10 millivolt resolution. Originally intended to convert digital numbers from GPIB to drive an analog data plotter, for example. I'm starting by disassembling it, naturally. There are 3 PCB modules in here, but since I can't find the service manual, I have to guess what they do and hope that things are working. The main PCB has a few electrolytics. They look a bit odd, so I better replace them. The mains input module doesn't have any capacitors internally, but rather 2 RIFAs are soldered onto the backside. Be gone! I had similar Y-class ones around. The closest ones I had around are quite a bit smaller than the originals, practically the same value and voltage though. That front panel seems a bit droopy. Apparently, the unit has been dropped onto the selection switch before. I need to straighten that. The front panel PCB has LEDs for the indicator lights. That is odd. Either somebody modded it before, or this unit is quite newer than expected. I wonder how long this was sold. And now, after putting it together again, calibration time. As mentioned, I couldn't find the service manual, but a website listed the calibration procedure at least. And here we go. Connecting the digital to analog converter to the bus analyzer, trying to get some voltage as an output. Now here's a good point to explain a few basics about GPIB. The bus has 8 data bits, usually labeled D1 to D8, but I've seen D0 to D7 too. It would be too easy otherwise. The bus can have up to 15 devices connected, but supports up to 31 addresses. This is because it uses 5 bits for addressing, and all ones are a special case. At any given time, only one of these devices is in control of the bus. The device that controls the bus is the one that can drive the data bit lines. All others need to keep them in read access. When the controlling device wants to send a byte to the bus, it first drives the data bits to the desired state and then sets the DAV, data available signal. At this point, every listening device knows that there is data on the bus, and it reads that data into a latch of sorts. Once the listener has the data, it releases the NDAC line. NDAC is not data accepted. It is driven low by all devices that are listening but have not yet read the data bus. When nobody is driving this low anymore, a pull-up resistor will make it go high on the bus, thus telling the controller that every device has successfully read the current byte. Similar to the NDAC line, there is also a NRFD line, not ready for data, which works in the same electrical way. It is held low by any number of devices who should listen but aren't ready for data yet. This form of handshake makes sure that the controller will only send bytes once each and every device that is listening can actually receive them. Thus, the speed of the bus, in bytes per second, is dictated not so much by a constant clock, but rather by the slowest device on the bus. This is how the data transfer works. But how does a device know if it should read data at all? Here is where another option comes into play: listening or at rest mode. Each GPIB device I came across so far has a set of configuration options, typically dip switches. One sets the listen or at rest mode and the other the address itself. In listen mode, the device will accept each and every byte that is put on the bus. No questions asked. This makes for a very easy point-to-point connection between two devices. But it also works for any number of devices. In contrast, the address mode needs a bit more control logic. The controller first needs to enable the device for listening. This is done by sending a listen address command on the bus. Only the addressed device will read and acknowledge that, turning itself into a listening unit and reading the following bytes. There is a matching unlistenAll command which uses address 31, hence that one is reserved. Finally, there are a few control lines. IFC, interface clear, is used by the controller of the bus to force a full reset. REN, remote enable, tells the device to go into the remote mode when they receive their data. ATN, attention, is used by the controller to indicate a command rather than data is on the bus. SRQ, service request, is asserted by any device to call for attention, kind of an interrupt request to the bus controller, which then needs to scan the bus, called serial polling, to find out who was knocking. To simplify things, I'll put the DA converter in listening mode, that way I can ignore the addressing for now. I want to have plus minus 9.99 volts and I want to read the rightmost 3 digits. What's with the digits? Here's where I had to do some sleuthing. Remember, no manual. As it turns out, the DA converter will read a line of ASCII text and then take 3 digits out of an up to 10-digit number for the output. This way, you can have the meter reporting on the bus and the DA converter can react without any controller in between. Now setting things up. I want the bus analyzer to talk and I want to use the memory feature. Typing in the program is a bit cumbersome. I want 7.32 volts output, so I need to key in the ASCII codes for 734 followed by carriage return and line feed. 067, 063, 062, 015, 012. But that last one also is the last of a string. That means I should also set the EOI signal too. EOI is AND or identify because it serves 2 different functions depending on the attention signal. Anyhow, after typing in the bytes, let's start. And here it is, 7.32 volts on the mark. Well, the millivolts are a bit fluctuating, but that's out the spec anyhow. Woohoo! Let's try the same thing with addressed mode. I'll set the DA converter to address 2. This automatically will listen to address 2 for data and 3 for the mode selection commands. The program in this case needs to read set listen address 2, send data string, and at the end, don't forget to unlisten. I'm sending 6.55 volts this time. And last but not least, I'm connecting the USB GPIB adapter and send off a voltage setting from my desktop PC. By putting the analyzer in bus mode and slow mode, I can delay the handshake. The analyzer pretends to be a very slow device by holding down the NDAC line. And that's it. Another vintage piece of test gear. Or rather, test gear even. I'm sure this will be useful at some time. Oh, and in case you are wondering why both of these devices are so weirdly primitive, neither has a processor or similar controller chip inside. Both are implemented with pure TTL logic chips and just a few bits of ROM for the character display. Anyhow, that's it for this episode. See you next time! I'm using a magic eraser again to carefully bring out the shine.